G'day and welcome to this lesson on sequence convergence. In mathematics, a sequence is a list of numbers that follows a specific pattern. The concept of convergence in sequences is a fundamental concept in calculus and real analysis. In this video, we'll explore the concept of sequence convergence and learn how to determine if a sequence of numbers converges to a specific limit. We'll discuss the difference between convergent and divergent sequences and see how to not only calculate the limit, but also prove it. So let's get into it. Here's a formal definition of a sequence that is mapping in a function setting the natural numbers to set x, where every natural number n is being mapped to f of n. And in this case, our natural numbers is specifically 1, 2, 3, all the way through to infinity. And we can define and represent these sequences in shorthand in these following forms. If you're being really punchy, you can just write xn in brackets. If you want to be very specific, you can do xn in brackets with n equal 1 all the way to infinity, or xn where n is a natural number, xn that's just written as a function, or you can actually write out the sequence directly, x1, x2, x3, and so on. And these are how we represent and portray our sequences. So to look at an example of this, we can have a look at the sequence where the function rule is n is being mapped to 1 on n, and then we can write it down in this format, any of those formats there. And if we take a look at the graph of this sequence here, we first plot n equals 1 to 1 as the output value, n is equal to 2 to 1/2 as the output value, and just using this rule we can go on plugging it in and notice that it is following this trend of getting smaller and smaller. And the question that we're often interested in when it comes to sequences is, what is the limit of the sequence? When n is getting large, what is the sequence doing? And is it following a specific pattern of converging to a number? Or does it just get out of control and diverge off to infinity? Or does it oscillate between certain numbers so it doesn't converge, but it's just going -1, +1, -1, +1. We don't know. And in this example here, we can look at our pattern of our sequence where as n is increasing, the value of xn is just getting smaller and smaller and smaller and smaller. And a lot of people, when you ask them what they would guess is the sequence limit in this context, they will say that the limit is 0. And people have a pretty good intuition as to what the limit is. And so the question here is, how can we actually rigorously define the limit and then use that definition to portray that the limit here is, rigorously speaking, 0? And that is when our sequence definition of convergence comes in handy. So for our concept of convergence, we're going to be using this definition here. A sequence xn converges to x star if, for all values of epsilon greater than 0, there exists a natural number n where every number that is greater or equal to n, when we plug that number into our sequence, the distance between the sequence and the limit is less than epsilon. And this collectively categorizes the concept of a limit. The idea of getting closer and closer to the limit, in this case 0, as you get further along in your sequence. And epsilon here is, when you see an epsilon in a economics or maths course, usually the epsilon is a variable that is specifically interested in small values. Of course, the sequence is for this epsilon definition holds for any epsilon, so you could pick a large one like 1 million or 2 million. But what is interesting is when epsilon gets really, really small and closer to 0. So the epsilon where this definition gets interesting is epsilon that is very tiny. And if your distance is being measured between the limit and your current sequence value, and you want that to be less than epsilon, and your epsilon is a small number, that means that you are very, very close to the limit. So just to maybe unpack all of these components here of our definition, because I know people can find it confronting looking at the symbols here, but we have this here. For every epsilon greater than 0, that's that part there, there exists some n, an element of the natural numbers, that's that part there, which for all n bigger than n, the distance between xn and the limit x star is smaller than epsilon. And yeah, the idea is to pick any epsilon which measures proximity to the limit, and we focus on those small epsilon values, and we're searching for some point in the sequence. So this idea of existing n in the natural numbers, where all n greater or equal to n blah blah blah, is saying, is there a point n where we can draw a line, we can literally draw a line for the sequence inputs and say all the sequence inputs beyond this n, so this part here, is going to satisfy this property. And the property here is that the distance between the limit and where you are at the sequence is within epsilon of each other. So looking at our example of 1 and n, we can apply this rule to it. This is obvious, but we're still going to look at it anyway because it helps solidify our understanding of this definition. If you have n, xn, and the distance between xn and x star, as x star is 0, the limit is 0, the distance between this and the limit is just going to be itself. And if we just take an example epsilon of 0.1, then we're searching for a point in our sequence where the distance between xn and the limit, which is this column here, is always within 0.1 of the limit. So if we draw the line here, we can see that as soon as you get to 11 or further into the sequence, this distance is going to be less than 0.1. So we provided a n in this specific epsilon case, and we want to generalize this to every epsilon, and in particular very, very tiny epsilon. And if we can do that, we're proving this concept of convergence, where we might not ever hit x star. It's never, it's not necessarily hitting x star because this isn't greater or equal to 0. If this was greater or equal to 0, then when epsilon was 0, your limit would be the function being at x star. It doesn't have to be like that, but you can always get arbitrarily close. You can always get closer and closer and closer to that limit. And what we want to do is prove this. Use maths to actually rigorously prove this. So let's take a look at an example of that. If we're proving this 1 on n sequence goes to 0, the first step that we want to do is figure out what epsilon relationship to n there is that satisfies the definition. So if we let epsilon be just anything greater than 0, what n should we pick to satisfy this rule? And the first step in proving sequence convergence is finding out the relationship between n and epsilon, finding the point in the sequence where you get within epsilon of the limit at that point and onwards. Once you've found that point using the scratch work, you then write it out and formalize it in a proof. Okay, so what we do is we cheekily just set the distance being less than epsilon, which is what we should be proving, but in our scratch work, we're just setting it like this, and then working backwards to work out, okay, if this was less than epsilon, what sort of relationship do we have going on here between n and epsilon that we can then achieve this going logically from here upwards. So set xn minus x star to less than epsilon. That gives us 1 on n minus 0 is less than epsilon, because the sequence limit is 0 in this case. That gives us 1 on n is less than epsilon because n is always positive, so we can get rid of those absolute values. And this little n in this case is talking about the sequence inputs n that are beyond our specific point of interest. So mathematically, we know that this little n has to be beyond the point 1 on epsilon. And then if n is greater or equal to the point we're looking at, and then the point we're looking at is greater or equal to 1 on epsilon, then we have this being bigger than this, which is bigger than this, which working backwards achieves our definition that we're looking for. So essentially looking for n here. We're going forwards with n bigger than that will satisfy the definition. And as long as this n is bigger than 1 on epsilon, then all of the n that follow it will satisfy this definition according to this scratch work here. So now that we've found our point in the sequence which will achieve this, we want to rigorously write it out in a proof. So to do that, the focus of this proof is proving for all epsilon greater than 0, blah, 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 blah. So we're going to start our proof by letting epsilon be an arbitrary value that's greater than 0. And then if we prove that it's true for this one, it's true for all of them. Okay, and we just worked out from our scratch work that we want to choose a natural number n such that n is greater than 1 on epsilon. As epsilon is never equal to 0, this is always a possible natural number. It always exists. Okay, and then we want to consider xn minus x star. So xn minus x star is equal to 1 on n minus 0, which is equal to 1 on n, which is equal to 1 on n without the absolute values. As n is greater or equal to the big N, 1 on little n is less than or equal to 1 on big N. So the denominator here is bigger than the denominator here, which means that the fraction is smaller overall. And then we know that the big N is bigger than 1 on epsilon. So for the same reasoning, this denominator is bigger than this denominator, which means this fraction is smaller than this fraction. And then that fraction is equal to epsilon. So that is equal to epsilon, which means this is less than epsilon. So maybe I'll say equal to here, depending on how you interpret this type of writing out. This is equal to this is strictly less than epsilon. And that means we've completed our proof. So we've shown that for all epsilon greater than 0, which is true because we did it for one arbitrary epsilon, there exists a natural number, which we find using this rule, that all natural numbers that follow that one satisfy that 1 on n minus 0 is within epsilon of the limit. So 1 of n is within epsilon of the limit, which is 0. I might just amend this and also say let n be greater or equal to big N. It's fine without it because I'm just discussing for all n being greater or equal to big N, but you could get rid of this and then just have let n be greater or equal to n, just a stylistic way of writing out the proof. It's not a big deal. Regardless, we've shown that this definition of the sequence holds, and thus we've actually proven it rigorously. Okay, last thing we're going to look at in this class is some theorems about sequence limits. And these theorems become really handy when you're trying to prove a complex sequence and its limit, because you can break it up into simpler things and then put them together to actually do a proof on a more complex sequence. So here we have the limit of a sequence plus a constant times a sequence is equal to the limit of the sequence plus the constant times the limit of the other sequence. So that's kind of like two theorems in one. The first one is that you can add limits, you can add sequences together and their limits. The limit of the sum of sequences is equal to the sum of the limits. And then also a constant times a sequence will have the effect on the limit of just being a constant times the limit. Next, you have two sequences multiplied by each other will give you a limit where x star is multiplied by y star. And that's for sequences xn that are in R. And that's also for, actually no, don't worry about that. Also, if xn is a natural number that maps things to Rm, which is a sequence output that has more than one dimension, so you could have a vector sequence, then the limit of that vector sequence is going to be the limit of every individual component of that vector. So if you want to prove the limit of that vector, you need to prove the limit of all of the components first. And that together will categorize the limit. Right, that's it. That's our video on sequence and sequence convergence. We can now extend upon this to actually heading towards continuity, which is an important part of real analysis. That's the end of the video. I hope you found it helpful.